everyone. Good afternoon. My name is Daniela Rus. I'm the director of the Computer Science and Artificial Intelligence Laboratory at MIT. And today I am delighted to welcome our very special guest, Pat Hanrahan, coming to us from Stanford, where he is the Canon USA Professor of Computer Science and Electrical Engineering in the Computer Graphics Laboratory. So Pat received his PhD degree in nuclear engineering, and his the BS is in nuclear engineering and PhD in biophysics from the University of Wisconsin. And today he is one of the most celebrated computer scientists with impact in teaching, in research, in entrepreneurial activities. So you see how important it is to have diversity of backgrounds and ideas and classes. Now, in addition to being a beloved award-winning teacher at Stanford, Professor Hanrahan is also an extraordinary entrepreneur. He was a founding employee of Pixar Animation Studio, where he was part of the design of the RenderMan interface specification and the RenderMan shading language. And this is really important because this work was used to create one of my favorite movies, Toy Story. When my children were little, we watched Toy Story to the point where I was able to recite the lines. And our daughters were so delighted by all the scenes. So thank you for that, Pat. Now, this work in rendering also received 3 Oscars. Can you imagine? I mean, we are seriously cool in computer science if we can go after Oscars. So I encourage you to think equally big, extraordinary thoughts. Professor Hanrahan joined the Stanford faculty in 1995, and he later co-founded Tableau Software, where he remains chief scientist. He is the winner of numerous awards. In 2019, he received the highest honor in computer science, the Turing Award. Congratulations. And he's also a recipient of many other important awards in computer science. He is a member of the National Academies of Engineering and also the American Academy of Arts and Sciences. Now, I, for one, greatly admire his ability to be so brilliant and visionary and creative as a thinker, and at the same time, so down-to-earth and warm human being. And we are really honored to have him today to hear more about his thoughts on where our field is going. So let's give him a very warm MIT welcome. Pat.
Thank you. Thank you. Yeah. Oh, she showed my slides, so thank you very much, Daniela. So really is a great pleasure to be here. I haven't been here a long time. In fact, I've never been in this building, and it's just great to see so many friends and colleagues here. So I'm giving sort of a maybe unusual talk for me. I mean, I'm actually sort of going to give you a little historical retrospective of what I've worked on. I mean, this is sort of based on my Turing Award lecture. I decided, there's lots of different kinds of Turing Award lectures. I thought I'd just sort of try to describe historically the facts, like what I actually did. So it's not there's not a lot of opinion in here. It's just sort of here's what I did, and I worked on it for quite a long time. So anyway, that's what I'm going to talk about. So I'm going to actually go back to the early days of computer graphics. So this is a picture made at Pixar, actually right before I got there. So I got there in 1985, and it was called the Road to Point Reyes. So if you've ever been to Northern California, maybe you've been to Point Reyes National Seashore. It's a really beautiful place. And the group at Lucasfilm, they were a part of Lucasfilm, was trying to convince George Lucas that they could develop technology to help him make movies. So they made this picture, and the idea was that this was just something he might have seen, like he could drive to Point Reyes in his little convertible at the time, and he might have seen this picture, and they were trying to convince him, like, we can make a real world. We could have a world with plants, we can have a world with water, mountains, and so on, and you could make a movie in a place like this. So it was just sort of meant to be, this demonstration to him that this technology had potential, and he was always somewhat skeptical of it, but it was also it was one of the first pictures made by this rendering system called RAISE, which Lauren Carpenter put together. And RAISE stood for Renders Everything You Ever Saw. So the whole idea of this was that could you build one system that could render all these different kinds of things? And there were, you had different kinds of materials, you had different kinds of shapes, like plants versus mountains. You had different kinds of effects, like atmospheric effects versus, say, surface reflectance. And so could we just build a whole system that would bring all this together and actually evolve forward so that you could add more different types of objects? So, that was sort of their goal at the time. And there was one other goal, and these goals are really important because when you're picking a technology problem, you need to have the right goals. So at Lucasfilm, of course, they were a special effects house, right? So they mostly did live action where they had cameras. So Lucas was a famous cinematographer, and they would have live action. They would superimpose special effects in it. And so they had you seamlessly compose these special computer-generated effects with the live action, and it had to look like they fit together. So this was one of their early examples of animation where they had young Sherlock Holmes. I don't know if anybody ever seen this film. It's a pretty obscure film. Yeah. Oh, okay, good. All right. But anyways, there's this stained glass man that jumps off the stained glass window, and the idea is, sort of see it's supposed to like seamlessly, like the same lighting, and so on. And there was also, you couldn't have any artifacts. So there's all these common artifacts like motion blur. You might not have motion blur. You could have sort of shuddering, or you could have depth of field because real cameras had depth of field. You could have aliasing or jaggies. And all these things had you sort of not be present in the computer-generated thing. And the final thing is, if you looked at that RAISE picture, it just turned out to be incredibly complicated. So here's one of the first projects I worked on. I was part of the team that was building what's called the RAISE machine. This was from a retreat that I was there at. I wrote down these notes from the retreat. And this was the specs for what we had you do. So we were making movie quality images, which were 5 megapixel images back then, which is pretty high resolution. I mean, back then you had like NTSC video, which was like 640 by 480. There was this thing called depth complexity, which is like how many polygons occupied every pixel. Then we wanted to have really tiny polygons because we had all this fine geometry. So we would break them into what we called micropolygons. So each micropolygon had to be smaller than a pixel, otherwise you could see the micropolygon. And that turned out to be 80 million micropolygons. And then we were really frugal. We said, suppose we did 300 foot operations per micropolygon at 24 gigaflops. That was just like inconceivable amount of computing at the time. I mean, you have to really go back to 1986. You can't imagine this. But it's important for me to tell you this because as a computer graphics person, my whole life has been living in a world where I wanted 1 million times more computing power than I ever had at my fingertips at any given point in time. And so that was sort of the world I grew up in, that we can't imagine doing this. And if you look at this, in 1986, Toy Story came out in 1995. It took about 10 years, which is a factor of 100 increase in computing power, roughly, before they could even consider making a movie, because of this thing. And if you look at, movies today, this is the last movie I've seen detailed stats on that's been published. But if you look at Monsters University, it's a pretty old movie, like almost 10 years old. It takes 29 hours per frame to make this image. Notice it's quite a bit more complicated image. But it's 100 million hours total of CPU time for this movie. And if you do the calculation, it's sort of amazing. It's about a gigaflop per pixel of computation that goes into this picture in this movie. So again, that's a lot of computing to do to make one picture, right? And so these things are really, really expensive. So anyways, our goals when I was at Pixar, my job was to build a rendering system that could handle the diversity of the everyday world. It could have incredible amount of geometric and visual detail. It could handle things like motion blur, depth of field, anti-aliasing, in other words, seamlessly composite images into real photographs. So sometimes we call that photorealistic rendering because we have to be completely realistic. And it had you map efficiently to hardware because it was sort of economically not feasible to do. So anyway, that's sort of interesting challenge, right? So I just graduated from my biophysics degree, and I started working there, and they give me this job, okay? Now, they had made a lot of progress on it. They had come up with this raised architecture, and I'm just giving you two papers, one that they wrote in 1987 describing the raised architecture, and then I actually just wrote a paper with Ed Catmull called The Designer Render Man that sort of goes through all the design issues that I had to sort of deal with in building this system. So I'm actually not going to talk about that today too much. Well, I just want to talk about one aspect of it, which was the shading language, because that sort of took another pathway through. But I encourage you might want to take a look at this paper, because I tried to, I'm really interested in design of software and hardware, and so this paper sort of I got all my notes and tried to, re-immerse myself in that world. Okay, so probably the most interesting aspect of the system from my point of view was this thing called the shading language. So again, I'm sort of giving you my personal retrospective on this. So here I'm one software engineer trying to support this animation group building this amazing rendering system, and I had like 40 pages of feature requests. And I said, I could sit down for the next 5 years and implement every one of these features, or I unfortunately know just enough computer science to say, or I could build a language and they could implement all the features themselves, okay? So, I knew that much computer science. So I came up with this shading language. And, why did I do this? Well, actually, this is a photograph of me in 1983 at the University of Wisconsin when I first discovered computer graphics. And I actually dug up my very first paper I wrote, a technical report in the computer science department. You can go download this, 1982. It was called Procedures for Parallel Array Processing on a Pipeline Display Terminal. And I just sort of dug this up because I actually built a language as my first project in grad school. I was working in biophysics, but I got an RA ship to build this language. And actually this language was designed to run on special purpose hardware, and it was designed to implement deep neural networks. My advisor, Leonard Ure, was an expert on what are called they called them pyramidal neural networks at the point in time. So this was a fairly hot topic in 1982, okay? And so we already had specialized hardware, and I was developing languages for it because that just seemed like the interesting way of doing it. So anyway, I was sort of already interested in developing languages that could run fast. But what are shading languages? Somebody asked me right before the talk. Well, there were two really important developments in graphics related to this. And the first one was by Rob Cook, when he wrote this paper called Shade Trees. And what Rob wanted to do was model different kinds of materials. So I showed some pictures of these vases he made, and he was just like, why does copper look different than, say, rubber, Or why are different metals, why do metals look different than like lunar dust, right? And he would develop various, procedural models that would sort of differentiate between these. And he wanted sort of a test bed so he could experiment with these various things. And so he had this little language, which was basically just expressions, which he could download these expressions into the rendering system, and then these different materials. Same geometry, right? Same vase, but each of these materials had these different shaders associated with them, and he could develop these different things. And so, at this point in time, there was a lot of interest in, procedural representations of geometry and appearance, not just sort of formulas, but, more algorithmic computing type things. And then the other paper that was really important, which was also in this same theme, was by Ken Perlin. This is a famous picture he made. He invented this thing called this fractal noise, which we still use today, Perlin noise. And he was interested in developing patterns. So there was shape, there was patterns, there was shading, and all these things could be, sort of described algorithmically. And so as a result of this, people became very interested in, how do I write these programs? Like, I want to embed these in the rendering system. I want them to all work together. How do I do that? And so this just seemed like a way of solving this problem of capturing a whole range of different visual phenomena with just a simple language. So this is the language sort of I came up with at the time. I mean, I'm not going to go through all this. By the way, this is total, I know some very accomplished programming language people in the crowd. and I'm sort of embarrassed to show my feeble attempt at designing a language without any training whatsoever, okay? But anyways, this is what I came up with, okay? But anyways, this language, this was one of my test patterns, this teapot. And the first part of the language is I'm just looping over, well, I had this thing called corrode, I have a bunch of parameters. And I'm just, different objects could have different parameters. So KS means how shiny it is and so on. Then I have this thing where I'm computing these bumps. So this is this Perlin noise thing I was talking about. I'm just summing up different octaves of noise. Okay, so noise is a band-limited function of noise. I'm summing those up. So that's a nice way of generating sort of this fractal-like noise pattern. Then what I do is I take that turbulence value I compute. Can't point at this very well, but take that turbulence value I compute and use that to perturb the position on the surface along the surface normal. So n is the normal and p is the position, and normalize just makes the normal a unit vector, and so I perturb it outward a certain amount. Then, now that I've perturbed the surface, I have to recompute the normals, because now the perpendicular to the surface has changed because I've perturbed the surface. So we had a built-in magic function, calculate normals from position, and then I finally compute the color of it, okay? So, you know, this is what the technical director types would do, is they'd write in these little programs like this. And, you know, it was a domain-specific language in the sense that it had all these useful functions built in for shading, right? It had this context like position and normal. So this function would get called by the rendering system at every point on the surface that it wanted to shade. So, and, you know, I mean, this is just, and, you know, just sort of one thing I've just learned in a lot of my projects is I like to take sort of a language-oriented approach to solving systems problems. You know, so, you know, you end up sort of learning about a domain, embedding it in a language with a bunch of high-level functions, and it's just sort of a fun thing to do. You know, it's a very, very computer science-y kind of thing to do, but it's really fun to do. And, you know, this just show you some other fun things about the language is, you know, in graphics we have light sources and surfaces, and light sources cast light, and surfaces reflect light. So here's some constructs like sort of like control flow constructs, illuminate and illuminance. And illuminate sort of casts light out in some cone. So it's sort of, imagine it firing rays of light out in different directions. So it's looping over this cone, centered at some position and firing light out. And then illuminance is sort of the reverse. It's like searching for light coming in from some cone and then using that to reflect off a surface and determine the color. And so you could write programs like this, and then you could develop new kinds of shading models and things like that. So, you know, just how do you do it? I'm not going to go into this in all detail, but, you know, it's a fun thing to do, is just figure out how to abstract these things. And of course, illuminate and illuminance are not something you'd see in C or some conventional language. And they have all sorts of interesting properties that you can take advantage of if you have a compiler and so on. And so anyways, I'll just show you, that's just an example. Okay, so anyway, so that's sort of what I wrote this language up. And we started using RenderMan, and it was really a useful feature because now, you know, well, it was useful for me because now I just had this language and they could implement all these 40 pages of procedures and features that they wanted, and it saved me a lot of time. Okay, so at the same time as I was doing this, sort of GPUs sort of emerged into the world, okay? So, you know, this is sort of ancient history, but some of you, it's good to know. Okay, so, you know, building GPUs is sort of an interesting thing that hasn't really received much attention in the computing world. I mean, in the sense of an engineering thing. Like, it's sort of a mysterious thing. There are these graphics architects in the world, and what did they actually do? And suddenly we have NVIDIA GPUs everywhere. But, you know, it took a long time to figure out how to do this. So one of my good friends, Kurt Akeley, who actually did his PhD with me, he joined SGI, and he actually built most of their early workstations. So he wrote a paper in 1992 just sort of describing how graphics systems were evolving. And he said there were these various generations of graphics systems. So the first generation things are like wireframes, like you see that, you know, airplane there with, you know, just lines. Then you had shaded polygons, which is the second generation, where you can draw, you know, fill in polygons, so you have efficient polygon rasterization. If you take graphics courses, you know what that means. You have hidden surface elimination. You have smooth shading, so you get sort of like smooth surfaces that look like they're 3D. Okay, and that was a big advance because now you had to like write to the frame buffer. You had to write all these pixels to the frame buffer. It's much more computationally demanding. Then you had this third generation where you added texture. And that I show a picture with texture mapping. Textures, you probably all know, you all play video games, right? Is just putting images on surfaces. But now as you draw that polygon, you have to look up that texture value, and you also have to filter it properly and all that. And that was enormously more computation. You know, so each of these things, you know, it was taken 4 to 5 years to have enough computer power to just do these simple steps, you know what I mean? And you know, we take them so much for granted, but they require unbelievable amounts of computer power. So this started happening. And then Kurt actually did this other project, which was to define OpenGL. So SGI started building these workstations, and they wanted some way of programming the graphics that was independent of the implementation. And so he came up, which was the OpenGL graphics pipeline, which I think we hopefully all know and love at this point. I mean, it's sort of fading out a little bit because it's being replaced with some other things. But you know, this whole idea that you send triangles down into the graphics system, they're made of vertices, they get rasterized to complete these things called fragments, textures get applied to them, and then they get merged into the display. And you know that if you take graphics, you probably learn about this graphics pipeline. But one reason I mention OpenGL, other than it's a really, you know, there's nothing that makes me happier than writing OpenGL programs. I mean, I just like to write graphics programs, and it makes me very happy. So I'm happy to even talk about it. But the thing about it, which people don't realize so much, is it's specified an architecture for a graphics system. So what does that mean by that? And by the way, I was just talking to Jonathan. I was just at UNC giving a version of this talk, and I met with Fred Brooks like literally two or 3 days before he passed away. But he wrote a book, a very influential book on computer architecture. In fact, he coined the term computer architecture, I believe, in his work on the IBM 360. But what he meant by computer architecture was it had some specification, abstract specification of what a machine should do. Okay, it wasn't a particular implementation. In fact, if you read his paper on the IBM 360, he says that, you know, we're going to do 6 implementations of this IBM 360, right? And this is the architecture. They all have to obey these rules. They all have to do these. They have to all execute the same instructions and so on. They all have the same 8-bit, you know, byte and so on. And so what, you know, this idea that there's this abstract specification of some architecture is what Kurt took on. He said, well, what does it mean to specify an abstract graphics pipeline? Well, I have to define the state. So just like if you have a processor, you have some state like registers or accumulator, and then you have to specify some instructions. And if you ever read a manual, like the ARM manual, it'll say if you execute the add instruction, here's how the state gets changed. So in the case of OpenGL, if you execute a draw a triangle command, which is like an instruction, it says how does the frame buffer change? It defines that really precisely. And so there's very much a similarity. You know, even though you're using these API calls, this idea that is you have this abstract state machine, and your architecture is a specification of how the abstract state gets updated independent of the particular implementation. And that's what you can see. As a programmer, that's what you see. So, you know, I mention this because, you know, people sometimes don't realize that in graphics we have architectures, just like you have architectures in processors, you know, but they're often specified a little differently than maybe we are used to with ISAs. So you had this graphics pipeline, you had this architecture, and then in 1999, the NVIDIA GeForce 256 came out, which is the first use of the word GPU that I know of. It was sort of a marketing term from NVIDIA at the time. But the reason they came up with this is they had implemented for the first time the complete OpenGL graphics pipeline on a single chip. Okay, so sort of like when you had the first CPU, you know, like that was the first single chip computer, right? This is the first single chip graphics pipeline. So now you sort of set in motion this world where you had these 2 chips, right? You had the CPU, which was executing your normal program. You had the GPU, which was doing all the graphics. And they were all about, similar technologies, actually. So I just mentioned this became possible when feature sizes got to 220 nanometers, and I'll come back to this, pretty large feature sizes. It only had 17 million transistors. But it's sort of interesting. I mean, if you look at like the first ARM processor, it had way less than 17 million transistors. So it took much more to implement the first GPU in terms of resources than it did to implement the first processor. So it sort of makes sense that they came later. And keep track of this number. So we'll come back to how big GPUs are, now later. But it's not that many transistors. I mean, we're talking about current chips having billions of transistors. Okay, so that sort of was happening, and I was following that. In fact, I used to work at NVIDIA a bit. But then, what could we do real-time shading languages? So I wrote a DARPA grant in 1995. So one thing that's sort of interesting about graphics, maybe, and this is another thing about technology, sometimes there's some things you can sort of do like in batch mode, like, like in time-sharing mode on a normal computer, and then they eventually get in hardware. So that means that there's some lag between when somebody can do it algorithmically and when you can put it in hardware. And that lag is pretty calculatable, right? Because you know how much computation it takes to do something, and you know how Moore's law is advancing. So you can predict pretty precisely when it's possible to do something in hardware or when the price is going to go down. And in graphics, I mean, this has been like at 10 or 20-year timescales, but all of us were very conscious of this in the field. We knew we could predict quite accurately when certain things would be possible. So in this grant in 1995, I just think, what can we normally do in software, and when could that go into hardware, right? So I proposed, this was sort of a riff on Kurt, and I might have even been advising Kurt at this point. But what could we do next? Like, what would be the next generation? And I said, in this grant, I said, well, we just sort of reproduce RenderMan, right? So this picture of the bowling pins is one of the first RenderMan pictures. And the main things were we had this shading language for doing lighting and shading, and then we had curved surfaces, not just flat polygons. And then actually in this grant, I actually claimed that the 5th generation was going to be ray tracing global illumination, which we had already done by that point in time. And you're now just starting to see that emerge in graphics hardware. So this was probably bogus. I mean, I just had you put something in there because it took a long time to get to this point, and there's a lot more detail that had to be worked out, and it still hasn't been happening. So I don't think this was a particularly good thing. But it was easy to make some general prediction like this. I mean, because we had already figured out how to do it. We knew about how much compute power it would take. So I'm not going to talk about that. But anyways, there was now this urge around this time to take things like programmable shading and get GPUs to do it. Okay, it was like a fairly obvious thing to do. So a bunch of people started working on it. UNC folks worked on it in a system called PixelFlow, a little bit in Pixel Planes, Mark Alano and Anselmo Lastra. SGI worked on it. In fact, they were funding some of our work, and they wrote a paper I'll tell you a little bit about called multi-path shading. Then we wrote with Keikoa Proudfoot, and Bill Mark on our real-time shading language. And then Bill Mark and Kurt Akeley, who, like I said, were very interconnected, then went to NVIDIA and implemented the CG system, which was very similar in spirit to RTSL. It was different in some ways I'll come back to. But over this fairly short period of time where you could suddenly start running shader programs on GPUs, and there was this intense interest in how to do it. Also, just to mention one other thing, sort of funny, you see this shading language thing comes up. Again, I have no training in languages, but I used to go around to all sorts of computer scientists saying, these GPUs are getting really interesting. Like, you should work on those, you know what I mean? And nobody, whatever, I mean, so, I think sometimes people just have to try to anticipate what's happening in certain fields and try to get in on the early ground. Otherwise, you end up people like me that don't know what they're doing work in this area, okay? Anyways, so the first thing that people realized was you could render things multiple times And we called that multiple passes, because every time you render something, we'd call that one pass. We'd like draw all the scene in one pass. And what you could do is you could just sort of layer detail on top. So this is an example of that bowling pin where you draw the background color with the single stripe, then you draw the Brunswick logo, then you draw a circle, then you draw some scuff marks, then you add the diffuse shading, then you add the specular shading. If you do each of this, one step at a time, and you end up sort of implementing an instruction set, sort of like. So you think of this OpenGL thing as this compute engine where you have the image or the frame buffer, and you take what's in the frame buffer. The frame buffer acts like an accumulator. You accumulate into the frame buffer what you're drawing. And what you do is you take the value in the frame buffer and you blend in the colors, and you can add in the colors, you can multiply the colors, you can blend them using like alpha blending and so on, and you can apply texture to them. But you can maybe only apply one texture. So if you can only apply one texture, if you need to apply multiple textures, you have to do multiple passes. And so this was the idea of interactive multi-pass programmable shading that Mark Piercy and Mark Lano and others worked on, where they basically realized that this thing is just a giant parallel array processing engine. We can just keep drawing over and over and over again and compute these parallel array operations. But on the other hand, SGI was doing that. People started evolving the graphics pipeline, and they went in a very different direction, which is important to think about. So what was also happening is you had this OpenGL graphics pipeline. What you could do is you could say, I'm going to take one little stage in that pipeline and insert a program in that stage, like the fragment processing stage. And that program, it gets fed the values, like in this case, from the rasterization engine that's outputting fragments, but then it runs a program on all those fragments and then combines those into the fragments. So you're just inserting like a programmable stage. And that programmable stage has access to textures and some state and registers and so on. And so, this is really interesting because it's probably was very contentious at the time, but really important concept, is this multipass stuff was very much like vector or array processing, where you would just loop over these vectors and do these operations on them. But there's a problem with this, is that it consumes a lot of memory bandwidth. Because you have to, like in this case, read a couple things and then do one operation and then write it. So, and the vectors are very large, so you're not able to cache them very much. So vector processing, even though it's like a really good idea, wasn't a very good match for these architectures. And at the time, we actually measured that. I think you could do 12 floating point operations for every floating point value you read. So, this was a tremendous waste of bandwidth, right? I mean, you just used all this bandwidth. And of course, you just had that you wanted to optimize bandwidth in order to make it work. So what you want is and Bill Daly actually, who used to teach here, and I were collaborating on this, we came up with this term at the time called arithmetic intensity because we were trying to explain this to people. But you want the number of operations you do compared to the amount of data you read and write to be as large as possible. So we call that arithmetic intensity. And it's the ratio that matters. It's not the number that matters. It's not how many gigaflops you have or teraflops you have. It's the ratio of your total compute to the total bandwidth. And this is really important, because especially when you have exponentials, if you just talk about one value, it's going up at some rate, but another value is going up at a different rate. That's dangerous, right? So, and that's always been the case for memory, but people just don't think in terms of ratios. You always should think in terms of ratios when dealing with exponentials. So anyways, we call this stream processing. It's almost identical to vector processing, but instead of doing like one operation, you do a whole function's worth of operations. And that can be like hundreds of operations or dozens of operations. So the original shaders had like dozens of operations, okay, that you could do as you ran them. And that was just enough to, then you could sort of amortize the cost of writing the value at the end, but you also got as many operations as you do. If you only did one, you were in trouble, but if you could do 10 or 12 or 16, you were golden. And it's a simple model, but it encouraged people to write much more efficient programs. So it's one of these little simple things. But that also means that's sort of why this SGI multi-pass pass approach just wasn't a good answer, and why the stream programming approach was a good answer. So these are just like examples of sort of design decisions you make, back to the Fred Brooks architectural thing. You have to have an architecture, and you have to make these sort of design decisions about it, and these are the big decisions you make as an architect. Okay, so there's one more part to the story. Well, then there became this general purpose GPU. So I worked on that. So that seemed completely obvious to me. So this goes back to this very place, right? I guess thinking machines used to be at Kendall Square, right? Just across the street, right? So I knew about the connection machine. I had read Danny Hillis's paper. I knew all the people that worked on the connection machine. Everybody knew about data parallel programming. And they had done that in the 1980s, I think, in 1985 or 86, I believe they formed that company. So this was a very well-known idea. But the people in graphics didn't necessarily know about it. But I knew about it because I had been doing data parallel programming. It's been around forever. So we started this project saying, could we make a GPU into a general purpose data parallel computer? And we were already mostly there, actually. If you think of this kernel thing, if you know functional programming, there's this thing called map, which is apply a function to all items in a collection. Right? If you ever use Python, you use map. So we are already doing that. If you draw a triangle, you generate a bunch of fragments, you apply this fragment shader to them, you've applied this function to all the elements, all the members of the triangle. So we had map. It also turned out another data parallel thing is like filter. By the way, these are all well known because Hillis and others had all come up with these really nice data parallel. Cray. I mean, this is all well known stuff. You might want to remove items from a collection. Again, if you know Python, you've seen all these functions. Well, it turns out we could do that as well because you could. We had these stencil things which let us conditionally write, and we also could kill a fragment so it didn't get right into the frame buffer. So you could do that. Another common operation is you want to take a collection of addresses and you want to load all the values at those addresses. Okay, this is a little trickier. So we call that gather. So that turns out, in some ways, we had that with this texture lookup. Because if you access the texture, you could read a value at some address. You think of the texture coordinate as an address. So you could read a value. But this actually turned out to be really important. So, and I've worked on multiple GPUs at different companies, IBM Cell Processor, Intel Larrabee, and this is what they all goofed up. Is if you look at the program you're running in that fragment shader, this is actually an example of an early fragment shader program. This was the assembly language for a fragment shader program. There's about 5 or 6 instructions, and there's one texture load in every 5 or 6 instructions. Because this is the one that the benchmark, you had to run as a benchmark. Just drawing a simple polygon with one texture. Well, you have this really short loop, and you're doing a random load, a load from a random address in the middle of this very short loop. I think there are architects in the room. They will probably start squirming about now, okay? Because, and by the way, I'm going to tell you, that doesn't cache because that's a random access to memory. So they sometimes call that a global access, global random access, like GUP or something. Like I've gotten grants from the NSA to work on this problem. You know what I mean? This is just a really well-known hard problem, and but we had you do it in graphics. We had you do these random accesses to textures in the short program in the inner loop, and that's what you need to implement this gather. Well, how did we do that? Well, the way we did that in these early GPUs is we had this texture, there's a microphone there, this texture prefetching architecture. What we did is we generate a fragment, and we say, you have to access texture. We put the fragment in this FIFO, this long queue, and then we go out and access the texture, and then eventually it comes back, maybe 100 or 500 cycles later, that the actual texture value comes back. And now what you do is this fragment's been percolating through this FIFO, and by the time it gets to the end of the FIFO, the texture's there. And then you merge it in, and then you're golden. So you just have to make this giant FIFO of all the fragments that are waiting for their texture values. Okay, and that's how people would build these early GPUs with texture mapping with these pipelines. It's not very well documented, but it's pretty much they all did something, some variation on this. Well, that evolved into multi-threading. So if you look at a GPU now, they have these things called warps. I'll tell you a little, but they have these maybe they're doing 32 pixels at a time. But what they do is they run a short program there, then they do a texture fetch, then they jump to the next warp, because they have to wait for this thing to come back. Then they jump to the next one, then they come to the next one. In fact, typically they might have 30, 48 or more of these warps. And the reason they're doing that is because they want to do this read for memory. And so you get this sort of what we would call multi-threading. There have been computers like this that have been built. Every time they do a memory access, they suspend this thread and do another, switch to another thread. In GPUs, they very aggressively did this because they had you. So this is a simple thing, but it made allowed GPUs to do gathers or random accesses to memory, which a lot of other computers like DSPs and so on were not able to do efficiently. And like the CSAIL and the Larrabee, they were not able to do this efficiently because they didn't build this into their architectures. So anyways, as crazy graphics people, and I can remember talking to the architects, I said, we're doing all this stuff. I mean, there used to be various camps. There used to be the multi-core camp, there used to be the SIMD camp, there used to be the multi-threading camp. Well, we need all the parallelism we can get. We're going to do all of it. And that was, and you have to get, but they all did that because they were just desperate to get as many processors as possible on a chip and write these programs that involved gathers. And so, that evolved into the crazy machines we have, where you have 16 cores. Those are like conventional cores. They each have their own thread. Each core is a SIMD thing, like with maybe 32 ALUs in it. Okay, so you have 16 cores, 32. That gives you like, whatever, 512 cores times, say, this, by the way, these numbers are from the first machine that really was like this, called the NVIDIA GeForce 8. This is the first machine that sort of created what we call the unified shader model, which was this sort of homogeneous set of multi-threaded, multi-core SIMD units. Okay, but anyways, but then at the same time, you also had 48 threads per core. So that gives you like that 24,000 threads that you have to have running in parallel in order to do all of this, right? And I mean, I think if you just go back to this period of time, if you were to talk to a computer architect and say, we're going to start requiring people to generate 24,576 threads in order to write a program on my machine, they would just balk, right? But you would go to the game engine guys, you say, do that, no problem. We'll take all that, we want all that processing. And we have to run those texture map programs. So, so that made these things pretty general. So anyways, it was fairly easy to just sort of knock off these primitives one by one. I'm not going to talk about the last two. Scatter is sort of the reverse of gather. And then there's a reduce or a fold or a scan, which is a good, famous connection machine thing. But anyways, pretty much all you could just sort of see the architecture could do this general purpose data parallel programming model. It had all the ingredients had been put into place. And so, that sort of, the last step was actually the easiest step in some sense. I mean, my student Ian Buck did this, and he did this thing called Brook. Brook stands like for stream computing, Brook stream. But all he did was build a data parallel virtual machine on top of the GPU, which was a fairly simple thing to do because you had all the primitives you needed to do it, and then you didn't have to be a graphics programmer. So and before then, you would have to know about, if you wanted to do map, you'd have to draw a triangle, and if you wanted to do this, you'd have to do texture mapping. Now you just have this virtual thing. It looks like a mini connection machine, and now all you do is you go to all the theses at MIT and how to do fluid flow, how to do databases, how to do this. It's all been done already, and so suddenly GPUs have this incredible range of applications that can run on that. And I'm glossing over some details. I mean, not all these things work right easily, but anyways, then Ian took his thesis and went to NVIDIA and implemented CUDA. So there, I guess maybe the only lesson is that, these old ideas like data parallel computing, you think they maybe were bad ideas because maybe connection machines and thinking machines wasn't a success, but they actually forged ahead and they created all this technology, and then maybe eventually things will get reborn, and we didn't have to do any of the work because they already came up with all the ideas. Somebody asked me at lunch, like, do you ever come up with any original ideas? And I say, no, everybody is always, actually, I saw the president of MIT, he came and gave a talk on the West Coast, and he said, we invent knowledge. And I thought that was a really great statement. Like, we create knowledge, which I really think you do. I think MIT is better than anywhere in the world at creating knowledge. And I utilize your knowledge, okay? I don't create knowledge. I don't know how to create knowledge. I use knowledge. I'm an engineer. Okay, so anyways, so, that's sort of an interesting story. So, it seems, I mean, it may be crazy. I just wanted to sort of tell it to you because to me it sort of seemed like an obvious journey, but, it was a long journey. Okay, so what are some implications of this for computing? Well, I think you'll probably get it. I'm a big fan of domain-specific languages. Saman, Jonathan, Fredo, also others here are in the domain-specific languages. I think they're the way to solve a lot of these problems. This is an early example I used. I think OpenGL, which is the library, is actually a domain-specific language. Because here's a little fragment of OpenGL code. Okay, you set up a camera with the perspective transformation, you draw some triangles in a loop, and then you swap buffers or update the image. Okay, but it's sort of, there's a grammar to it, right? Like if you want to draw a triangle, you have to say GL begin, you have to output vertices, you have to say GL end, a vertex has a color, a normal, and a position. There's a little grammar for OpenGL. I mean, it has a syntax. If you do things in the wrong order, you used to get a blue screen, okay? The GPU would crash, okay? So you have to obey this grammar. So I claim that's a language. It's embedded in C as function calls, but it's still a language. It has a grammar. But why is this a good thing? So I said, well, what we did in the early days of graphics is we programmed the GPUs with OpenGL. We didn't program them with like low-level CUDA microcode. And that means OpenGL, it's really easy to use. Everybody was able to harness all the power of it. It was very portable. You could run it on different platforms. You could run it on different vendors, right? NVIDIA, AMD. It performed really well. I mean, these OpenGL things would run incredibly fast. And it encouraged a lot of innovation. I think at the time, the reason graphics vendors were able to innovate so much over a period of about 5 or 10 years was because they didn't have to implement C. They could just come up with a completely different program. When NVIDIA switched from unified shaders from these special purpose fragment shaders, they were able to just do that, and none of your programs, none of the users were affected too much. I mean, there's always a little bit of transition there, but most things just worked. Whereas if they were really low level, it wouldn't have worked. So I think people underestimate how much programming at a very high level enabled these high performance GPUs to evolve. And that's not what happened in CPUs. We kept programming them at a very, very low level, and there was just no way they could do radical things. And then they started doing crazy things like, execute 16 threads speculatively and stuff like that. But we were able to go much more efficiently. Then the second thing I'll just mention, which I think GPUs are sort of an example of, is the now huge interest in domain-specific architectures. Everybody knows about end of Moore's law. We can argue about that afterwards over beers if you want. But it's clear we're getting sort of near the end of traditional transistor scaling. But I think Dave Patterson was here a couple years ago. He probably gave this talk. But you would think this would be the end of the world, right? Moore's law ends, we're doomed. Why are we studying computer science? That's the end of the golden age of computing. Processors are going to stay flat, we're doomed. The whole field's going to it's going to be like cars. They'll just get, be sort of stable technology for 100 years. But these guys have this other idea that, we're going to enter a golden age of computer architecture. And, their argument is that, there's lots of room for optimization by having domain-specific architectures, customized hardware, right? And you see that's what's happening in computing. This is the latest Apple M1 Max. But, there's all these specialized units here. I'm not going to go through all the details here. I will mention that in the center of that is this giant GPU, by the way, which is way bigger than the CPU, which, EA GPU. But anyways, but there's also all sorts of other stuff in there. There's actually two kinds of ARM cores. There's these high-performance ARM cores. There's low-performance ARM cores. There's these neural processors. There's all this stuff for video and audio and other things. There's all these specialized units in it. I can't even get a number, but I think people say there's 50 or 60 specialized hardware units in this chip doing all sorts of things. And so you're already getting an incredible specialization in these chips. And this just sort of shows it. Once you get up, this thing has 57 billion transistors, right? I mean, you can't get away with a single core, right? I mean, if you go back to that example of the first GPU, it was 17 million transistors. So now we're at 57 billion, So you can put an entire GPU on 17 million and an entire processor on maybe a couple million. So you gotta, consume this real estate, and you're gonna do it more and more with specialized units. And so I'll claim these specialized units are domain-specific computers. They're gonna be somehow specialized for various tasks. And maybe going back to my background in biology, like in biology, there's not just one organism or one species. There's many species, many organisms. We have this rich ecosystem of living things. And I actually sort of like that view of the world, rather than having one thing like beetles. Like if the world was just filled with beetles, it'd be a pretty boring place, okay? So we want all this variety. So I think that's actually really exciting. So now we can build domain-specific languages and domain-specific architectures for all sorts of different tasks. And I actually think that'd be really, really a fun thing to do if I was in computing longer. So, all right, so I'll just tell you a few things to summarize my journey. First of all, I was really lucky to work on a really challenging problem, which was how to do photorealism efficiently. I mean, it just, some problems are too easy, some problems are too hard. This one just turned out to be just hard enough to take about 10 or 20 years, but not too hard that we could never solve it. I actually never thought we'd solve it because I thought it was like AI. I thought AI would not be solved. We can argue about that too, but I didn't think AI would be solved in my lifetime, okay? Anyway, so that's good. Second is you want to utilize appropriate hardware and software abstractions. Maybe go back and read Fred Brooks' paper. But I tend to think I learned enough that I like to use language-oriented APIs. I think those are really good ways of building systems. I like to use parallel architectures because I think hardware is intrinsically parallel. And so I latched onto those things. I was very fortunate. Those were the good technology trends to, I think, ride. And then I'll just finally say, specialization is going to become much more common in computing. And, I think a lot of computer scientists are sort of afraid of that. They like general purpose things. I like general purpose things. But general purpose things don't always solve the problem efficiently. And so sometimes, we might just have to entertain more specialized solutions to problems. And, that just means we have to be a little more application focused. And that might be a hard transition for a lot of computer scientists because they're used to all these really simple general things. That might be difficult. Okay, great. I think I'm out of time. Thank you very much.
So let me kick off the Q&A with a question. Do you think we still need to learn to program? Isn't GPT-3 going to write all of our programs?
You guys ask hard questions. I think we're still going to be programming for a while, yes. Although I'm excited by the automating programming, but yeah.
So, as you started this, you said you could sort of predict in advance when certain things would get into hardware, the pace of course will fall. And I think we have known for a very long time that as we have more and more parallelism, we require more complexity to integrate things to get the right communication between CPUs, memory, etc. So projecting forward, we'd like you to use your crystal ball and tell us now how many DSLs are we going to have? Or let's say 20 years. That's going to be long, right? So 20 years from your 80s. How many DSLs will we have? How many separate kinds of cores that will be supporting those will we have on every processor chip in a
Okay, well, the first question I get asked that a lot, okay? So I actually have a prepared answer for that one. Second one, I don't, but actually, the way I always throw that question back at the person, I say, how many libraries do we have? Libraries. Yeah, I mean, we invent these libraries because they each encapsulate something we need to do, like text processing and numerical computing. And, we have, I mean, literally tens of thousands of APIs and library calls, operating system calls, networking calls. And, so we already have to deal with this problem of a huge number of domains and a huge number of interfaces. So I think that's how many we'll have. Maybe we can narrow those down, but we have a similar design problem. I think by making some of those things smarter, like the halide examples, they used to have these image processing libraries, and they got really complicated because they weren't smart enough, you know what I mean? And now we have languages like halide that'll let us build those libraries much more efficiently and more generally and more adaptively and more powerfully. So I think the DSLs are going to actually decrease the number of libraries we have substantially. And how many DSLs there will eventually be, I'm not really sure. I mean, how many animals are there? I mean, each one sort of is designed to specialize for some niche, So where are the niches? I'm not sure it's easy to predict, but there will be some natural distribution of them, but I don't know exactly how many. I think as computer scientists, we want to make them as general as we can, but not too general, right? I mean, that's my attempt at that answer. So.
Questions? From the students? Yes, right here.
I guess, so you started off doing a lot of sort of non-real-time rendering, and then it seems like a lot of this innovation that you talk about is like stuff with shading languages, which seems to focus more on real-time rendering. So I was wondering, how did you sort of make the transition between those two domains, and did you find that shading languages were helpful at all in your?
Yeah. So I mean, I think. Well, that's a great question. Thanks. And, some of these questions make me think because I don't analyze myself as much as I should, perhaps. But I think I got interested in real-time graphics because I just thought that would be more ubiquitous. Like if you look at this offline rendering, I mean, Pixar is, everybody knows Pixar, but they don't make a lot of money selling rendering software. It's a fairly high-end niche thing, building, making movies. Whereas, games, I mean, graphics libraries run everywhere, right? I mean, that Apple GPU runs on every laptop, and it runs on every phone and every. So I think I always sort of realized that graphics would be ubiquitous, or at least I wanted it to be ubiquitous, and so that's why I was always led to the, GPUs, real-time graphics. I just thought it would be more ubiquitous. So I don't know. Was there another part of the question? I forgot, but yeah. Mm-hmm.
Okay, one in the back.
Yeah. So right now, the world, and this is with technology, it's growing dramatically in the amount of stuff that is out there at a rate that I would argue we haven't really seen before. This leads to a ton of different areas that one can choose to specialize in. how would you go about making that choice?
Oh, well, okay. You guys are asking me like really, make me feel really old. Okay. Anyways, I don't know how I would make the choice. You know, I will say, when I made some of my choices, I was looking for a new thing. You know, like I was in physics, and you know, physics was a pretty well-established area, and so on. And you know, it was a really fun. I really enjoyed it. But I got interested in computer graphics because it was like wide open. You know what I mean? Like, it didn't really exist. You know, graphics when I was doing that stuff on that terminal really didn't exist. I mean, you can't imagine it, but in 1980s, you know, frame buffers cost like hundreds of thousands of dollars, and we couldn't imagine a world of, you know, making movies and games in real time. So I was drawn to this fact that it was a new area, relatively unexplored, and so I think that was how I made those decisions. I think as I moved on in my career, I actually mostly worked on stuff other people didn't want to work on. I mean, you know, I tried to get all these people to work on general purpose GPUs. Nobody wanted to work on it. I wanted them to do this. Nobody. I mean, I just knew I was, you know, in areas I didn't know anything about, and nobody else would work on it. So, well, if they're not going to work on it and nobody else is going to work on it, maybe I'll work on it. So, you know, I think it's surprising how often there are really hot things that nobody works on. You know what I mean? I mean, they just, so if you just can find those things, and I did a lot of work in visualization as well, which you mentioned at Tableau, and it was mostly because nobody was working on it. I mean, you know, at the time, just nobody was trying to apply visualization in the general, to databases, you know what I mean? Just nobody was working on it. It seemed like an obvious idea, but, you know, nobody was working on it. So, you know, if you look for these areas where people, that are really interesting problems, the world is filled with interesting problems, and nobody is working on them, and you have some ideas, that's a pretty good combination, I think. So that's the closest I can come to that answer, I think.
All right, last question.
You mentioned that specialization is the future, but for instance, hardware is really hard to design, test, and fabricate. So what sorts of infrastructure do we need in place before we can develop specialized systems?
Wow. Geez, you're my friend. Okay, so that's what I'm working on. So if I was to give a talk about what I'm working on now, that's what I'd be attempting to answer that question. Okay, so when I talked to John Hennessy and David Paris, said in order for this to actually work, we're going to have to lower the cost of hardware development enormously. And hardware, it's costly for many reasons. I mean, you know, some of them intrinsic reasons about physical design and fabrication. Some of them is because they're using like languages like Verilog and ancient technology that is just ridiculously bad, you know. So, you know, there's tremendous room for innovation. I mean, you know, it's not like, you know, they haven't been in, I mean, I gave a talk once called "Why Can't Hardware Design Be as Easy as Programming?" You know, which, by the way, programming is not easy. I mean, you know, we all know programming is really hard, but hardware design seems to be infinitely more complicated than programming. So I don't think there's any reason for that. I mean, most hardware designs are just programs of a certain language, certain domain-specific language. And so I think there's tremendous opportunity to improve hardware design environments, and I highly encourage people to work on that, because if we're going to build all this specialized stuff, we need better tools. Yeah, great question.
So Pat, thank you for being here with us, for taking us on this historical and very interesting path, and for telling us how to think about our work so we can get the next Turing Award. Okay, off to work, everyone, and don't forget, focus on hardware design.
Exactly. Thank you. Thank you.